This is a video to guide you through the simulation exercise. There's three parts to this. One is that you're going to plot a normal distribution. Second is that you're going to simulate the random movement of a large number of particles. And then you're going to plot a frequency distribution of those particles to compare to the normal distribution. And you're going to see how both those distributions, the normal distribution and the simulation, develop over time. The first one of those things then is to plot the normal distribution. You've done this already. Previously you've plotted a unit normal distribution where you've distributed an area of 1 throughout the distribution. This time we're going to distribute 500, because in the simulation that you'll do subsequently there will be 500 particles. So to make them match, rather than making it a unit normal distribution, we're going to distribute 500. So the Gaussian equation is already written into the spreadsheet for you, and we can click on the formula bar and you can see there's the formula, and the parameters of the formula are the x value, which will be distance. We need to enter some x values, and then also the standard deviation. Standard deviation squared has actually been extracted from the formula and placed in a single cell. That's because to simulate time we're going to change the value of the standard deviation squared, and it's easier to do that by changing the number in a single cell rather than in a whole column of formulas. So the standard deviation squared is referred to in the formula rather than the number being written in. It's been referred to by the cell address as an absolute cell reference, because we'll be copying that formula down. So what do we need to do? We need first of all to come up with our x values, and we're going to be plotting the normal distribution between minus 100 and plus 100. So our first x value will be minus 100. Then we can choose the step size that we want to use. To have a similar resolution, we'll have 500 steps in our distance, which means instead of having step sizes of 1, we'll have step sizes of 0.4. So our second value will be equal to the first value plus 0.4, and we can just copy that down. And if we go to about 500, we end up with our value of plus 100. So we've gone from minus 100 to plus 100. Then we just need to copy our formula down. At the moment we've got a standard deviation squared of 0, so that's why we're getting divided by 0. We change that to 1000. Then we get a distribution, and the distribution automatically plots up. And that happens because in this column, the frequency normal column, we've produced a frequency distribution, and we've done that by summing up the area under the curve between H22 and H46, which is the first of 20 equal divisions along the x-axis. Next number, sum between H47 and H71, H72 to H96, H97 to H121. These have been written in for you to save you doing it, but what's happened is that the x-axis, the distance, has been separated into 20 equal classes, and then the area under the curve for each class has been summed, and then a frequency distribution has been plotted. If we check at the top, we've got the sum of each of these. This is the sum of that whole column, and we've distributed 500, so it should equal 500, which it does, very close to. This value is not 500, it's 1250, and that's because we need to multiply by the size class, which is what has happened here. We've multiplied by 0.4. And when we multiply by 0.4 and then do the sum, it comes to 500, close to 500, and that's the data that's been plotted for you. So you can try changing the standard deviation, or the standard deviation squared. If you reduce it, you can see the distribution becomes narrower. The passage of time, we would expect it to increase. So that's 1,000. We increase it to 2,000. Distribution flattens. We'd like to automate the change in the standard deviation squared so we can observe what happens over time, and that'll be part of what we're going to do in the next section, which is to carry out the simulation of the random movement of particles. To make the simulation requires us to do three things. We need to generate a large number of particles, we need to find a way to make them move randomly, and we need to allow that to find a way to progress that through time. So the first one of those things is to produce a large number of particles, which is very straightforward because we're working on a computer. What we'll do first of all is to give each of those particles an ID number, which will be important for us when we actually want to plot their movements, which will appear on this figure. So we'll just give them a label, particle number 1 to 500. Easily done. Just copy that down. .500 particles created. Now we need to consider how we're going to get them to move randomly. This is going to use a feature of computers, which is their ability to generate random numbers. They're not actually random, but they're pseudo-random, which is something we can discuss at another point, but effectively you can generate random numbers. To access that capability in Excel, we use an Excel function, which is rand, R-A-N-D, and then the argument, we've got no argument in there, just in the brackets, and what that will do is to produce a random value between 0 and 1. We need to think, how can we use that capability to generate randomly either +1 or -1, because that's what our particles to do. We want them to move 1 unit left or 1 unit right, +1 or -1. So to do that, first of all we need a starting point. So all the particles will start at position 0, so we give them a starting position. So our 500 points will start at 0, and then we need to refer to the starting cell. So we've got our starting position of 0, and then we're going to add either +1 or -1. So to use the random number generator, in order to generate either +1 or -1 randomly, we need to use another Excel function, which is a conditional statement, which is an if statement. So if the random value between 0 and 1, if we multiply that by 2 and then subtract 1, we're either going to have a number that is greater than 0 or less than 0. So if it's greater than 0, then we want to enter a value of 1. If it's less than 0, we want to enter a value of -1. So that's the way that the if function works. We put the logical test, which is random number multiplied by 2 minus 1 greater than 0. And if that's true, then we'll enter the value of 1. If it's false, we'll enter a value of -1. So that's the way that we can use the random number generator function in Excel, which generates a value between 0 and 1, to actually randomly generate a value of +1 or -1. The formula is entered for you in the text box there, so you can look at it again if you like. But what we need to do now is to enter it and then copy it down. And you can see then these particles have plotted the 0 line. Some of them have moved 1 unit to the left and some have moved 1 unit to the right. The way you generated a large number of particles was just by copying down. A way that you could generate a large number of cycles of calculation would be to copy this column horizontally. So we could select this column and drag it horizontally to simulate time. It's not the most efficient way of doing that, and what we're going to do instead is to use another capability of Excel, which is actually a fundamental capability of computers, and that's really why we're going to use it, so we can get used to the process of iteration, which is basically doing calculations over and over again. If we were to copy this column to the right, it would be inefficient because Excel would be creating lots of spreadsheet cells, each of which actually take up a lot of memory, and all we really want to do is to do a very simple calculation. So what we want to do is to repeatedly make the calculation in the same cell, and that's the process of iteration. To do that, what we'd like to do is to change this formula so that it refers to itself. At the moment it refers to the cell next to it and adds to it. If we could make the cell refer to itself, then the calculation would just go on within the cell. In order to do this, we need to change the settings in Excel. So we need to go to File, Options, and then on the Formulas tab we need to change from Automatic Calculation, which is what you're used to in Excel, which is when you enter a formula it automatically calculates the answer, but we want to make the calculation manual, and we want to enable iteration. By having manual calculation and enabling iteration, it means that a cell can refer to itself and the calculation will proceed for a set number of times, and the number of times that it will recalculate within the cell is set by default to 100, and we'll leave it as 100. After 100 times of doing the calculation it will stop, or the calculation will stop if the difference between one cycle of calculation and the next is less than 0.001. Again, the user could change that, but we'll leave that as it is as well as the default. We'll be examining these again, this maximum change known as the error tolerance, and we'll be examining that in another exercise. It's important to note that when you change those options, then they're saved with the spreadsheet, and if this happens to be the spreadsheet that you open first when you open Excel, then all other spreadsheets you open will have the same settings, and that will probably annoy you because you'll expect the spreadsheets to operate in the normal way, but they won't. So when you enter a formula it won't calculate. When you recognize that's happened, you can check by pressing F9. F9 is the button to make it manually recalculate. So now we can go back to our formula, and then instead of referring to cell C22, we can make cell refer to itself. And we can copy that down. You can see that these numbers are all the same, and that's because they're not calculating until we tell them to calculate. And you do that by pressing F9. Alternatively, you can go on the Formulas tab and you can press Calculate Now. So if you press Calculate Now, then what's happened is that 100 times the calculation for that formula has been carried out 100 times within that single cell, and you can see the result as we're plotting these points. They started all at 0, and after 100 random movements of plus or minus 1, they started to disperse. The majority, of course, is still in the middle. In order for us to compare this distribution of our simulation to the distribution by the normal distribution, we need to turn this distribution of particles into a frequency distribution. And so we can use the frequency function in Excel, which you used before, and we can put that in here. If you remember, it's an array function, which means that you need to highlight where the equation is going to be written first of all, and then move to the formula bar, put equals frequency, and the arguments that are required are the data array, which is this data, so that's your whole data set. We know it runs down to 522, and then the bins array. These are the data bins, which are used also for your normal distribution. We can close the bracket, and then as an array function we press Control Shift and Enter, and that's our frequency distribution. Until we press F9 or Calculate Now, it won't appear on the graph. If we press F9, then it will. So we now have a normal distribution, and we have a simulation of the movement, the random movement of a large number of particles. However, we've just in making the simulation, we've actually got the particles to move, and we've not really been observing. We need to find a way of initializing the simulation so we can start it from 0. We don't know how many iterations have taken place either. So to address those things, we need to have a way of stopping and starting the simulation and also reinitializing it, and that will require putting some numbers into these boxes and also counting how many iterations have gone on. So we're going to have a switch which is going to be on or off, and we can put a value in there of 1. If it's a value of 0, then it will be off. And we're going to have an initial value of 0, which will return all the particles to their starting position. Now, in order to make those things active, we need to return to our formula, and we're going to need to use another conditional statement to enclose our random movement formula. So we're going to have another conditional if the switch, which is this cell, and we need to make sure that's an absolute reference because we're going to be copying the formula down. So if B14 is true, so that's if it's a value of 1, then we want our random movement formula to run, so we can leave that as it is. If it's not true, then we want to enter the initial value, which is this cell. Again, we need to make sure that we make that an absolute reference. And then we can copy that down. Now we can check if we turn our switch off, if we make that 0, enter that, nothing happens because manual recalculation. So we need to press calculate now. If we do, then we've reinitialized because we put a 0. We put a false value, we put 0 in our stop and go, we've reinitialized. So now we can actually monitor the progress of simulation through time. The only missing thing is we haven't got a counter to tell us how many iterations have gone on. We know every time we press recalculate it's 100, but it's not easy to just remember how many times it's been pressed, so we should have a counter. And there's another reason we want a counter as well, because the counter is our measure of time passing, and our standard deviation for our normal distribution should be changed as time passes, so it should be linked to the passage of time. So that standard deviation, we should make it equal to our time value. So first of all, let's work out how we're going to enter a formula that allows us to calculate how many iterations have taken place. Again, we're going to use a conditional statement. If the state of our switch, if our switch is true, B14, we don't need to make that an absolute value because we're not copying it, but if B14, then what we're going to write in the box is 17 plus 1. If it's not true, we want to write 0. Okay, and then in B17, which we referred to, we want to write equals B16. Okay. Now, this counter should now increment every time an iteration takes place, and it's therefore our representation of time, and therefore we should link that with the standard deviation. The simplest way of doing that is just to make it equal to the standard deviation. So let's do that to start with. We can make that equal to the amount of time. Okay, and then if we press calculate now, we'll get to our initial situation. There we go, our initial situation. We're getting all zeros for our normal distribution because we've got a 0 standard deviation. And we've got all our particles lined up on the starting line at 0, and that's showing in our frequency distribution as well. So then we just need to turn our switch on, put a 1 in to make it true, and then press calculate now. Go. And you can do that again, and then you can determine how similar the normal distribution, the frequency distribution from the normal distribution, is to your simulation of the random movement of particles.